let me go back and review some material just as a review. Okay. Suppose you have an equation system that fits into this form, AX equals D, where A, of course, is your coefficient matrix. And let's just assume this coefficient matrix is n by n, where n could be any number, 2 or more. It's going to be a whole number. X is n by 1, D is n by 1. A is your coefficient matrix, X is the vector of your variables, and D is your vector of right-hand side constants. So suppose we have an equation system like that. If the determinant of A equals 0, what does that imply about a matrix A? Matrix A is said to be what in this case? Do you recall? Andra? Well, the rows and columns of matrix A are linearly dependent, but what about matrix A itself? Matrix A, in this case, is said to be singular. Okay. Matrix A is singular. That's really just a definition of what a singular matrix is. A is singular. And these arrows go both ways. That means these two statements are equivalent. If the determinant of A is 0, that implies A is singular. If A is singular, that implies the determinant of A is 0. So these arrows go both ways. That means these two statements are equivalent. Also, if the determinant of A is 0, Andra, we could say what about the rows and columns of matrix A? We could say the rows, then I'll put in parentheses columns. The rows, columns of A are what? Diana? Linearly dependent. Okay, one of the rows could be expressed as a linear combination of the other rows. Linearly dependent. Okay. We can also say this. If the determinant of A is 0, then what about matrix A? What can we say about A inverse in this case? Does not exist. And then one final statement. I'm running out of Blackboard, but one final statement you can make is, what about a solution to AX equals D? It does not exist. So this also implies that a solution, let me be precise, a unique solution to AX equals D does not exist. Okay. And actually, the book has a nice table. I'm really taking this right out of the book, where they go through this. Okay. So those are all the things you can say if the determinant of the coefficient matrix is 0. Now, just to, again, summarize and review, suppose we find this. Suppose the determinant of A does not equal 0. Then that implies A is non-singular. So all I have to do is put a non in front of the singular. Okay. The rows and columns of A are linearly independent. Means you cannot express one of them as a linear combination of the other. So I have to change this dependent to independent. And what about A inverse? What about A inverse? It exists. So I have to erase the not. A inverse exists. And I probably should say just A inverse. Let's get rid of the does too. Put an S on here. A inverse exists. And what about the last statement? A unique solution to AX equals D does exist. So get rid of the not. Okay. All right.